Hi, my name is John Paul Raj, and I'm on a mission to make the learning of math fun. So if you're new to this channel, please do consider subscribing. This is going to be the first video of a series of videos on the topic of differential calculus. And on this particular video, we're talking about rates of change. So let's start. We'll start with the slope of a straight line. So I'm going to draw a straight line first, okay? What color shall I use? Here we go. That's a straight line, all right? And I'm going to take any 2 points on that line. We all know that the slope of a straight line, if this is the point A and that's the point B, A having coordinates, let's say x1, y1, and B having coordinates x2, y2, then the slope of the straight line normally is represented with the letter M is given by y2 minus y1 over x2 minus x1. Okay, the difference in y coordinates divided by the difference in x coordinates. This is the slope or the gradient. Sometimes we also use that word. So it's either known as the slope or the gradient of that straight line. One thing, let me clarify, you can even write this formula as this is equivalent to y1 minus y2 over x1 minus x2. Okay, and that there is some truth to this. Okay, there is some really powerful truth that emerges from that. That actually means that it really doesn't matter which 2 points you use. You can even interchange those points and the slope of a straight line is going to be constant. Slope or gradient of a straight line is a constant. No matter which 2 points you pick up on that line, you're going to get the same value for the slope. Okay, that's the idea. And so in this particular example, even if you flip the points, A and B and B and A, right? But be consistent. If you're starting with y2, the x coordinate, that's the consistency, the corresponding x coordinate. So if you're starting with y1, which means the y coordinate of A, then the denominator will also start with the x coordinate of A. All right. So that's where you need to be consistent. If you're starting with the y coordinate of a certain point, then the denominator must start with the x coordinate of that very point. And then, as I said, this is the beautiful truth for the slope of any straight line. The slope or the gradient of any straight line is a constant. That's clear. We must have studied this in coordinate geometry. But what we're interested in is the slope. What's the meaning of the slope? What is the meaning? Some textbooks also use this word rise over run. Rise over run. Rise over run. It's literally like measuring how much does a line rise, how much is that inclination, how much is it rising. Can you see that? That line is rising. So if that's the ground level, how much is it rising? There's also a certain angular aspect to that rise. Is that right? Yeah, so we have another version for the formula of the slope. We also know that the slope of a straight line is also equal to tan of that angle, tan theta. That theta is measured in the counterclockwise direction from the x-axis, okay? So how much does that line rise and for how long does it rise? How long? So that's how long and how much. That's called the rise and that's called the run. Okay, so in other words, basically it's a difference in y coordinates, difference in x coordinates, but the meaning, the interpretation is that it's the rate of change. That's something that you need to know. All right, so anyone who asks you, what does that slope mean? You need to say that it is a rate of change, the rate at which quantities on the y-axis, whatever the quantity in the y-axis is, how much does it change? What's the rate of change of the quantity on the y-axis with respect to the quantities on the x-axis? So if I drop some axis here, okay, if that's the x-axis and the y-axis, let me label that. That's the x-axis, the y-axis. And let's just say that we've got distance. The distance is the quantity on the y-axis and time is the quantity on the x-axis. And let's say that we have a straight line relationship for distance and time, okay? And time being positive, I'm not taking anything on the negative side, all right? So that's the line. Let's just assume that this is a line that represents some kind of a relationship between the distance and the time. Quantity on the y-axis, that's what I want to focus on, okay? The quantity on the y-axis is distance in this case, and the quantity on the x-axis is time in this case, okay? The slope, remember what we said, the slope is a rate of change. So when we find the slope of this line by taking, any 2 points, y2 minus y1, x2 minus x1, that's the formula. But the meaning would be the rate of change of distance, because that's the quantity on the y-axis for this case, right? Rate of change of distance with respect to time. WRT is just short for with respect to, but we are identifying what's on the y-axis and what's on the x-axis. So giving it a context, rate of change of distance with respect to time. There's another nice word for that, right? That's called speed. So depending upon the context, in this particular, the context was, the quantity on the y-axis is the distance, the quantity on the x-axis is time. Depending upon the context, the slope of a straight line takes a new meaning. And that meaning, in this case, is speed, but the general idea is still rate of change. That's the first thing that we need to understand, that the slope of a straight line, yes, that formula is y2 minus y1, but there's a meaning. The meaning is rate of change. Clear? Let's move on. That's for a straight line. And here we go. Can you see this? All right, this time it's in blue. And that's my x-axis, my y-axis. And let's just assume we've got a curve, something like this. All right, and we'll call this a function f of x. Cool? F of x, just any function. All right, we don't know what that function is, how it is. We'll now draw a line that cuts this curve in 2 points. Okay? Now, this line that cuts a curve in 2 points is called a secant line. Secant line. And because a secant line is just a line, it's just any other line, this line also, you can find the slope of this line, right? Just by using the same technique, you can find 2 points on the line, and you can find the difference in the y coordinates and the difference in the x coordinates. We don't know what the quantity is, we just know that f of x, right? So let's find the slope. What would it be? So if this was the point we're going to choose, let's say we're choosing this point of intersection here, this point of intersection here, because that's how a secant is defined, right? It cuts the curve at any 2 points. And so what we're going to do is that, let's just say that the points are, this is a point A here. This point is going to have this x1, and this is going to have its x coordinate as x2. As such, the y coordinate here for this one will be f of x1, and the y coordinate of this point would be f of x2. Correct? Now let's make use of those notations and write down what is the slope of the secant line, right? So the slope of the secant line using these notations now, but the same formula, all right? The y coordinate, okay, so let's choose this point first, okay? So this point which has coordinates x2, comma, f of x2. Can you see my annotation? Oh, it's gone. Okay, that point has x coordinate x2 and y coordinate f of x2, and this point has its x coordinate as x1 and the y coordinate is f of x1. So if when you use the same formula for the slope, you will get f of x2 minus f of x1 over x2 minus x1. Can you see that? It's just become, it looks scary, all right? But it's the same formula, right? It's the same formula, y2 minus y1 or x2 minus x1. Same thing that we study in 8th standard, but now with that f of x, but f of x is just the y value, right? It's just the y value. So whatever was the x value, the x being the input, the y value is its corresponding output. It's the same formula as we've seen before, y2 minus y1. So it's f of x2 minus f of x1 over x2 minus x1. Same formula we've used. It just looks a little different and sometimes scary, but it's the same idea, okay? Slope of the secant line, f of x2 minus f of x1, x2 minus x1. Cool? Now let's put a certain context to it, and suppose that this graph actually measured the distance. Let's take the same example, distance. And here we have time. The meaning of the slope of the secant line, to understand that, let's get back to that graph earlier we saw. That was a straight line. Okay, the secant line is also a straight line. Well, that straight line in the first case represented the distance time graph also. So the graph was, that green graph represented the distance time graph. Here, it's that pink graph. That is the distance time graph. We are looking at the slope of the green line, all right? So that you need to be clear. That pink graph is the distance time graph, and that green line, that secant line, is actually intersecting that distance time graph. In this case, it's a curve at 2 points, all right? So that's the difference. Here, the distance time graph was a straight line. Here, the distance time graph is a curve, but that secant line is that green line, all right? That's the difference. So what does that mean? In this case, the distance is changing at the same rate. At the same rate. That's what we meant by saying that the rate of change of a straight line is constant. The rate of change meaning the slope, okay? So the rate at which the distance is changing, in this case, is constant. The speed is constant. That's what we meant in this case. Whereas in this case, look at the pink graph. The rate at which distance is changing is not a constant. It's a curve. That's why it's a curve. And so we have this secant line, the green line. We're looking at the slope of the secant line because you know what? The slope of the curve would be hard to find, right? Because it's always changing. So we're making use of a secant line this time. Secant line meaning it is intersecting that curve, that distance time graph in two different points, okay? So how would we interpret the slope of the secant line in this case? Well, it's a rate of change for one because, slope measures the rate of change. But because it's intersecting the distance time graph in those 2 points, it's going to be the rate of change between those two values of x. It's almost like saying because we are taking time as along the x-axis, it's between that time period, x2 and x1. As such, the slope of the secant line gives us the average rate of change. In this context, it's the speed. So it's like saying it's the average speed. The slope will always measure the rate of change, but because the secant line is a special kind of line and it intersects that curve, in this case, the distance time graph is a curve, it intersects in between those two values, in between those 2 points. So the slope of the secant line has to be interpreted as the average rate of change or the rate of change or the rate at which the distance changes between those 2 intervals of time being along the x-axis. And so we say it's called the average rate of change between those 2 values. So now let's think about what's going to happen if in that journey, if it was a journey, if it is a car journey, what would happen that instead of a secant line that cuts the curve between 2 points, you had a line, something like, let me take this yellow color this time, a line that cuts the curve. Let me draw a point there. A line that cuts the curve at exactly 1 point. Okay, my point's gone. So let me just draw that. Yep. Almost as, that's the best thing I can do, guys. All right. So this line cutting the curve at only 1 point, that's called a tangent, right? That's a tangent. So that's your tangent. Okay, let's call that T. And this line, green line, let's label that with yellow and call it the secant line S. So just like the secant line, you can also find the slope for the tangent line, right? You can pick up any 2 points on the tangent. You can pick a point there. You can pick a point there. Use the same formula, y2 minus y1, and find the slope of the tangent. And every line, whatever the slope is, it's still going to measure the rate of change. The secant line, because it's cutting the curve in 2 different points, we can interpret the slope of the secant line as saying that it's the average rate of change because it's over that time period. But what would happen if we were to interpret the slope of the tangent line, because it's only happening at that instant of time, because the slope of the tangent line is also going to be a rate of change, a certain rate of change, a certain rate of change of distance, but it's only cutting the curve at 1 point. And in this context, that 1 point refers to a certain instant of time. So the slope of the tangent line, is still a rate of change, but it's going to be the instantaneous rate of change. Same idea, okay? It's the same idea because the secant we saw is intersecting that curve in 2 different points. So basically, the interpretation is that, hey, it's a line and the slope of any line is the rate of change, but because it's intersecting at 2 different points, it's the rate of change that's occurring in that interval. But a tangent, on the other hand, it's also a line, so you can find the slope of that line also using y2 minus y1. But because the tangent line is intersecting only at 1 point, it's like saying it's at that instant of time. And this instantaneous rate of change, which is the slope of the tangent line, is also known as the derivative. So what is the derivative? Well, it's actually the slope of the tangent line. And what is the meaning of the derivative? Well, it is the instantaneous rate of change. In the context of the distance time graph that we saw, if the slope of the secant line, the average rate of change gives us the average speed That's the average rate of change, the slope of the secant line. Then the slope of the tangent line, which gives us the instantaneous rate of change, would give us the instantaneous speed in the context of the distance time graph, that is, okay? What that means is if you're driving a car, okay, if you start measuring the time, okay, this is the time that we started the journey and this is the time we ended the journey. And if you know the distance, then the total distance divided by the time taken for the journey, that would give you the average speed, correct? That's like that idea of the slope of the secant line. But anywhere during the driving, during the course of the journey, when you look at the dashboard, there'll be a speedometer that indicates the instantaneous speed. That is the idea of the instantaneous rate of change, which is also known as the derivative. Now, the derivative is a very, very, very powerful concept, instantaneous rate of change, okay? Even in cricket, for that matter, or any sports, when the team batting second in cricket, that is, they have something called an asking run rate. When they come to chase, there's something called an asking run rate. They keep that in mind. That's like saying the average run rate, like that average rate of change throughout the entire 20 overs. This is the T20 World Cup going on. For the entire 20 overs, there's an average run rate. That's the average rate of change, the slope of the secant line. That's the asking run rate when they've come into bat. But with every ball, with every fall of wicket, you will see that the asking run rate keeps changing. That's the instantaneous rate of change. That is the power of the derivative, the instantaneous required run rate. A wicket has fallen, couple of dot balls. What is the instantaneous required run rate? Well, at the start of the innings, when they came into bat, there was a different run rate, but now things have changed. It is important to know the instantaneous rate of change. There are applications of the derivative also in other fields like business. There is a certain rate of production. Something has been produced. A factory has been producing something on an average every month. But now you want to increase the production because you want to increase the profit. So every month, what should be the new average production rate? And if this is how much we need to produce every month, what should be the instantaneous? That means every day, what should be the rate of production? So the derivative is a very important concept. This idea called the slope of the tangent line giving us the instantaneous rate of change. We're going to continue this discussion in the next video. Don't miss that.